Proof by cases is common in mathematics. Here is an example. Suppose we want to show that n squared plus 7n is even for all n. A possible proof proceeds as follows. We know that every number is even, that is of the form 2m, or odd, that is of the form 2m plus 1. Let us take an arbitrary natural number n. Case 1. N is even, that is n is 2m. Then n squared plus 7n equals 4m squared plus 14m, which is again 2 times left parenthesis 2m squared plus 7m right parenthesis, and this is clearly even. Case 2. N is odd, that is n is 2m plus 1. Then n squared plus 7n equals left parenthesis 2m plus 1 right parenthesis squared plus 7 left parenthesis 2m plus 1 right parenthesis, which equals 4m squared plus 4m plus 1 plus 14m plus 7, which is 4m squared plus 18m plus 8, that is 2 times left parenthesis 2m squared plus 9m plus 4 right parenthesis, and this is clearly even. So in either case, n squared plus 7n is even. So n squared plus 7n really is always even. The structure of the above proof by cases is the following. We want to prove that n squared plus 7n is even. We know that n is even or odd. Note that this is a disjunction. We also know that if n is even, then n squared plus 7n is even. And also that if n is odd, then n squared plus 7n is even. And that is all we have to do. We are convinced that n squared plus 7n is even, whether n is even or odd. Proof by cases. If we analyze further what is going on in the above proof by cases, we can think of it as an application of a rule of this form. We know A or B, and we can prove C if we assume A, but also if we assume B. So, since A or B is established, we are convinced of C. In proofs by cases, we make temporary assumptions. In the above proof, the temporary assumptions were n even and n odd. In a natural deduction, we can make temporary assumptions, postulate a formula which is not an assumption, as long as we are able to eliminate the assumption at some point. When a temporary assumption A is eliminated, it is put into square brackets. Eliminating a temporary assumption is not always necessary. It is a right, not a duty. However, a temporary assumption which is not eliminated remains an assumption of the deduction and usually ruins the goal of the deduction. It is important to learn to distinguish assumptions and temporary assumptions from each other. Temporary assumptions arise typically when we know a disjunction and we want to make some conclusion. Then we temporarily assume first one disjunct and then the second to see what happens. In the above proof that n squared plus 7n is even, we knew that n itself is even or odd, but we did not know which. So we assume first that n is even and then that n is odd. We are ready to lay down the rules that govern disjunction in natural deduction. Disjunction introduction rules are very simple. From A we can deduct A or B, and from B we can deduct A or B. The disjunction elimination rule is more complicated, but we have just discussed it. The assumption is A or B, then we take A as a temporary assumption and derive C, and we take B as temporary assumption and derive C, and then the conclusion is C. And the temporary assumptions A and B can be eliminated. The disjunction introduction rule is rather obvious. If we know a disjunct, we know the disjunction. It is the disjunction elimination rule that is more interesting and features the just discussed proof by cases. The idea is that if we know A or B and we know C, whether we make the temporary assumption A or B, then we can conclude C. As an example, we derive C from the assumption left parenthesis A and C right parenthesis or left parenthesis B and C right parenthesis. Let us first think why C follows from left parenthesis A and C right parenthesis or left parenthesis B and C right parenthesis. Left parenthesis A and C right parenthesis or left parenthesis B and C right parenthesis says that A and C or B and C or perhaps both are the case. But whether A and C or B and C is the case, we have anyway C. So let us write the derivation of C from the disjunction of A and C and B and C. It is one big application of disjunction elimination. We just have to use conjunction elimination to take care of the temporary assumptions. Introducing disjunction. We derive left parenthesis A or C right parenthesis and left parenthesis B or D right parenthesis from the assumption A and B. Let us think intuitively why left parenthesis A or C right parenthesis and left parenthesis B or D right parenthesis seems to follow from A and B. If A and B is the case, then both A and B are the case. From A follows A or C. From B follows B or D. So we have left parenthesis A or C right parenthesis and left parenthesis B or D right parenthesis. Now we build the required natural deduction for deriving left parenthesis A or C right parenthesis and left parenthesis B or D right parenthesis from the assumption A and B. We attempt to use the conjunction introduction rule. In order to get A or C, we need to apply first the conjunction elimination rule to get A, and then the disjunction introduction rule to get A or C. The same for B or D. Here we derive A from A or A. This is a somewhat singular case, but note that we are now dealing with deductions that also computers may use. It is obvious to us that A follows from A or A, but it may not be obvious to a computer. Also, there are logical systems, for example so-called dependence logic, where one cannot derive A from A or A. In dependence logic, the disjunction A or A is satisfied by a quote team unquote X if and only if X can be represented as a union Y union Z, such that both Y and Z satisfy A. And a team X may very well satisfy A or A without satisfying A. Roughly for a similar reason, why €5 may be the exact fare for 2 tram tickets, but not for 1 tram ticket. Here is the deduction of A from A or A. Note that A is both the assumption and conclusion of the one-sentence derivation A. This is a singular deduction, but a deduction all the same.